I am Apurva and I'll be taking week 7's tutorial. Just a second. Okay, so before we start with this week's tutorial, let's just quickly take a recap from what we talked about last time. There were two themes in the last week's tutorial and the lectures. The first theme was if instead of allowing the space of strategies to be, or the policies to be just Markov, what if we let it be history dependent also? History dependent randomized, or just history dependent but deterministic? What happens in that case? So we saw that because of the structure of the problem, Markov deterministic is optimal and it is actually enough. We don't need to expand to the whole history, and nor do we need to know randomized policies over that history. So just Markov deterministic is enough. This was the first result that we saw last time. Then we went to the next question, which is if the MDP itself or the problem itself is such that the state is not visible to us, or the state is not known to the controller or the one who's deciding the controller controls, then what happens? Meaning, if it is a imperfect state type information, then what happens? How do we deal with such a situation? This is where we had a basic introduction, then an example, and this was the last thing. So we saw that then we'll have to worry about the whole history. So one thing that will change is not apart from having a state, we will also have some observations about the state. These could be either noisy observations or some linear dependent uh, part of the observation itself, but something which will not allow us to know exactly what was the true um, state. We'd have only an observation. That observation may be something we can use to infer about the original state, but will not be able to infer with complete confidence. There'll be some amount of uncertainty. So this is one more input of one more uncertain thing in the whole mixture. When that happens, then we talked about what is the kind of information that would be available. So at each step, the information would be the observation, and it'll be followed by the decision taken, the action taken, U0, and then the next observation. So this cycle would continue. And now, since this information is similar to a history, even though in the previous problem setup we said that history was not relevant, but in this particular problem setup where the states are not known to us or the state information is imperfect, then this type of a history in the form of information is actually important and we can't do away with it. But if we keep the whole history, then the form of the problem has changed completely. So, to take it back to our original form, to treat this as a MDP type problem, we talked about something called a reduction. That we can reduce our problem, we can introduce a new state, and we can say this IK, so history up till the information history up till kth time step, that is our new state, and whatever is added is the new information that we got, which is okay. So we got to know something in the current step and whatever we had up till that point. So this starts behaving like a state, and then this is the addition in the state. Then the whole problem can be treated like a standard MDP or a stochastic control problem. And further on, we can actually solve for the optimal cost. We can use DP for it and go through with the whole process. The only catch is while we are doing DP, we have to remember now what information is available at any given time horizon. It is important. This conditional on the information and the action, obviously, both of those things, this changes the kind of cost that we can actually work with. This shows up in the form in the DP algorithm as well. And this is happening because this observation, the Z, we are treating this as a parallel to a noise in our problem. Comparing this, comparing our new problem to a standard stochastic control problem, then this ZK behaves like some kind of a noise term. And here the noise term is not completely independent. In the original version, the WKs were IIDs, but here there is some dependence, and this dependence is given IK UK, ZK plus 1 will be independent of Z0 till ZK, meaning there is some dependence with at least some part of the information, not the whole thing. So with this kind of a structure introduced, we need to keep this part in mind, that some there has to be a conditional term that is coming up in the whole problem setup itself. Then a problem was solved in class, um and in this problem we noticed that if we have to solve for any simple version also, the number of different types of information, like at the level of say time horizon 1, the different versions of information, the different versions of histories that could have led to that particular point are quite a lot. And computing for all of them and then making a suggestion, then coming up with a strategy, it's a very tedious task. So, can this be simplified and generalized in other settings? That's the question that we are starting our today's lecture with. Okay, so today what we are going to do is we're going to use whatever idea and whatever notion we have of imperfect information problem, control problem, and apply that to a linear system, the LQ system that we had earlier. Okay, so before I start, in today's lecture, the plan is that I'll very quickly go over the things that were discussed in the video, this week's video, week 7's video, and then I'll take a couple of examples to motivate the idea more cleanly, and also to illustrate how this can be applied in slightly different settings. So I'll brush over these things a bit fast. I have the notes ready. If you have any questions, you can stop me at any point of time. Okay. So we are focusing on a linear system with quadratic cost and imperfect information. Meaning this is our main dynamics. This is how our xk is evolving with respect to xk plus 1 is evolving with respect to xk, uk being the control and wk being the noise. And this is for all k from 0 to n minus 1, so for all the time steps. Then our quadratic cost is the same kind of cost that we had earlier. But note here, if it is a problem with imperfect information, then there is going to be some observation. And let's say that observation is this zk, which is linear in xk, and there is some noise term vk. This is standard. This is the kind of stuff we saw already, because we've already seen linear quadratic type systems before. This is the only new term. And in fact, in the tutorial last time, we tried to work through this also. So we know very well what these kinds of things are. Then here CK, AK and BK are some deterministic matrices, meaning we know the things in the matrix. There's nothing to learn there. It's known, and the values are like they're numbers, they're real numbers. And the QK this one, this is positive semi-definite. There's a reason why people always take this to be positive semi-definite. This allows us to have a clean and nice form of the quadratic cost. This allows us to have some values coming up. It can be positive definite also, that is more strict, but we don't mind if this turns out to be 0 for some particular x, as long as r is positive definite, always positive definite. On the other hand, we do want these to be more like, all of these things to be more like squared terms, which is why we're taking them to be positive definite. We don't want the minimization to be unbounded. That's the idea that I'm trying to get at. Now, if we were to use dp in this problem, okay, right. Here the noise terms, both of these are noise terms, the wk and the vk. Both these noise terms are independent, have zero mean, and have some finite variance. And also they are independent of the initial x0 value. Okay, in that case we can start writing the dp algorithm for this. So for the dp algorithm, in such a setting, it starts with n minus 1 time step. So in this time step, all we have to do is we have to just plug in the values. So first we write down the stage wise cost at n minus 1. So xn minus 1 q xn minus 1, and then this term where the controller takes effect. And along with that, there is the j term. So this one, this is something similar to jn of xn. Let's say we have not assumed it to be 0 to start with, so this is what we are putting out here. And remember, since we are talking about a situation with imperfect information, we need to be very clear that we have some conditional coming up. So the conditional is on n minus 1, the information up till n minus 1. So this information is basically, so I n minus 1 is, it has observations starting from 0 till n, if we are actually even assigning observation at the nth point in that case. Otherwise it's till n minus 1. And the action starting from u equal to 0 till u n minus 1, sorry, n minus 2, one before the current one. It's after we have seen the information, that's when the action is to be taken, which is what we are actually minimizing over. Now remember, noise is something that is independent. So noise is going to be also independent of the noise wk is going to be also independent of this information. So the expectation of noise given the information just reduces to expectation of the noise, and we have taken the noise to be of 0 mean. So this term is 0. And another term, so another term over here, which is this term with this component with the rest of this component. So a term like this, or the opposite kind. So this version with this, meaning where there is just one wn minus 1 term. When we have a situation like that, again, because this variable, I've made a error here. because this variable is independent of x or u. This is just noise and it's not dependent on anything. We would just be putting the expectation separately on both of them. The expectation of this guy, expectation of w, is 0. So the whole thing will end up becoming 0. This simplifies our previous term. So first term stays as it is, second term is as it is. Now there is a term with, there's a term which is wn minus 1 transpose qn wn minus 1. This will not go away because covariance is finite. So this term will exist as it is.
One doubt. When you say you separate the omega, actually this expectation is on xn also.
Sorry?
Like previous statement when you mentioned,
This part?
since on omega is the independent of the other quantity, we
Uh-huh.
can segregate the expectation. I
Yes.
agree,
Yeah.
but the expectation will get split into two pieces, right? Because the
See, okay.
expectation over
Right.
xn also.
So it's this way, right? And then the remaining thing.
Yeah,
The remaining is this.
yeah. Now it will be zero.
Right. Now, since we already know this one is equal to 0, the whole thing becomes equal to 0. Better? Yeah,
Yeah.
okay. That was a slightly hand wavy argument. Acceptable?
Yeah, but
Okay, so next is just putting all of these terms together and keeping the ones which where there is some minimization on un minus 1, and the ones where there is no minimization, putting them separately. So that's just the next step. Right. Uh, First of all, from here, after removing these two terms, the remaining terms will be, this is intact here. This term is this along with this part. And remember, w does not have any dependence on the this part. So even though it's there, we have broken it down. We've used the chain rule type argument in expectation here. Then there is the term which has x transpose qn x transpose, this one with a's. That term is there. Then it's the remaining term which is this one along with this component. So here there is the component where there's a u square type term happening and there's a u times x type term happening. All of that is put together. Now the yellow and the green are basically pointing out the ones where there's just x's. These two have just x's, so this is one kind of term. And another is where there are u's because the minimization is over u's. So cleaning this up a little bit, we get the yellow ones together come up in this form. The green ones which are highlighted, so these two together become this. This is copied from here. And now one more term is the following. This is basically bun transpose qn with this component. This is just transpose and written the opposite way, but that doesn't change anything. It's the same thing. Now notice this one and this one, they have no dependence on u n minus 1. These are just x's, the true states at n minus 1 time. It's the action will lead to u x n, the terminal state. So there's nothing, no dependence here on un, neither is it here. So these two terms can be taken out and the minimization can be on the remaining terms. So minimization is on this term and this term. And just like before, if we do the minimization, it's a simple minimization, reason being it's quadratic, it's strictly convex and quadratic. So we just have to take the derivative and simplify. And when we do that, we will get, okay, let me remove this part, write it again. Right, when we do that, we would get un star to be something that will depend on the information structure up till that point. So it will depend on in minus 1. And what that actual quantity is this guy. And if you notice carefully, this is what we had gotten in the case without any imperfect information also. This was lk, l n minus 1 rather. In the lq with perfect information, it was the exact same first component. So here there's a lesson, and this lesson is the crux of this particular week's lecture, that you could get the optimal action even in case of the imperfect state game by using what we had in the perfect state, perfect information state LQG version. We don't need to use that same thing. The only difference here is there is a conditional expectation of the state given the information. That's all that's there. So the optimals are matching up to a certain minor variation. And one more thing that we had seen before was the presence of the W, this W. The presence of the noise term in the description is not showing up in the optimal strategy, or the optimal policy, or the optimal action rather, which is happening here also. So meaning there are these three games, there are these three different problems, and they have a way to go from one to another. Meaning if we, so okay, let me just add a little bit here. Let me draw it like a diagram. So our current example, what we were solving, this is only up till jn minus 1, in minus 1. This is how far we have reached, but still this is our argument up till now, that in the LQ control problem, with imperfect information, the action, the optimal action depends on some L term, some x n minus 1, I n minus 1 term, where this L term is actually common if we were to work with the LQ control problem with perfect information. So where there were no observations or anything. Then also what we got was very similar. So there was a ln minus 1 and there was just xn minus 1. If this idea that we got the same behavior, same structure going from perfect to imperfect game, if this holds in general time steps also, this is a very profound result. And in the lectures, it was actually shown that this does hold. The third case was, so this is case 1, this is case 2. There was a third case, this was also something that we had seen earlier. This is again the LQ problem, the LQ control problem, but without noise. Without noise meaning the WKs were not there. They were 0 by default. No noise term. In that case also, the optimal actions were matching. The optimal actions between the noiseless case and the noisy case were still the same. And now we are able to see that apart from this minor difference where we have to, instead of looking at just the state, we are looking at the expectation of the state given the information up till that point. If that's what we are looking at, then these are still very similar. And this is fair because in the case with imperfect information, we don't know what is the value of xn minus 1. We can only estimate what it could be, or we can only have a belief on it using whatever information we have so far. And that is exactly what this term is doing here. Meaning, if we were to deal with such a scenario, and if this holds in general for all Ks, then all we need to do is we just need to worry about the LQ control problems without noise. This is all we need to solve for. We can find our optimal actions here. We can use that in either of those settings. Here we have to make a minor change, here there is no change whatsoever. The minor change is because we don't know the actual states. Okay, so this is so far established for n minus 1 time step. Now next point is to see if this holds in general or not. So to see whether this is something that happens in general or not, you would look at the J value, the optimal J value. So after simplifying and all that, okay, so just like previously we had those K terms come up, P terms come up, we have some similar terms come up. Now if we were to compare this J term with the perfect information case, then we'll notice that there was no such term. This last term is the extra thing. These two are common. So all we need to justify is what happens because of the presence of this term in the recursive scenario. If that is something that we are able to justify, we're good to go. So the same process is repeated. Now the only difference is there is one extra term to worry about. And notice up till n minus 1 step we have information I n minus 1. If we are going to time step n minus 2, the information available up to n minus 2 will be slightly different from what is available at n minus 1. N minus 1 would have increased by two more information factors. One would be the observation and the other would be the action. So now let's look at this scenario. This is extending it to the time step n minus 1. For now, I have just written down the stage-wise cost, which is these two terms, and then the jn minus 1 in minus 1 term. Now this is the term that we have to use from the previous part. And like I'm saying, these two are present even in the case of uh, LQ problem without any observations, or where there was no imperfect information. Only this term is extra, so we need to very carefully focus on what this term is and what does it even mean. Okay, let's first look at this term one more time. This term, if you notice carefully, this Pn minus 1 is some kind of a, at least a positive semi-definite quantity. It's going to be very easy to prove that this is because Qn and Rn minus 1, both of these are semi-definite, positive semi-definite. This is going to be symmetric, and from there on we can prove whether this is um, semi-definite or positive semi-definite. Okay, so this is more like a distance type of a scenario with respect to that matrix. So now here this is xn minus what is our belief of xn given the information we have so far. So this is more like a error in our estimation of what is xn given the information that we have so far. If that error is very small, this whole term is like a contoured, distorted mean square. Distorted. So we just want to know if this is something that plays a role further on or not. One possibility is that this error between the actual xn minus 1 and the estimated xn minus 1, or the belief of xn minus 1, could get accumulated and would become a very big problem, and hence apart from just the very simple case of n minus 1 step, these three problems will not have any further correlation between them. But we already know that these two are same for all k's. This is for all k values. What happens here is the part that we are trying to establish now. Alright, so now let's notice each of these terms carefully. This first term, on this term we have to take the dependence with respect to in minus 2 and un minus 2. But un is the action that is taken after a state has been realized, after there is some true state xn minus 2, meaning this will not be affecting xn minus 2. So we can drop this conditional for this term. Next is the following: the expectation over this given all of this, meaning it's the realization is already there, we don't need to worry about the expectation. So this is just the original term itself as it is. Right, and now we're going to start plugging in these values. Remember, jn had three terms. These two are the common terms. This is the one that is the term that we're going to anyways focus on for a while. So the first term from jn minus 1 in minus 1 component is the cost wise term, the stage wise term, which is the following. Now here it has converted to kn already. Notice what happened here. What is I n minus 1 as compared to I n minus 2? What is the difference between these two? The only difference is there is a z n minus 2 here, the z n minus 1 actually, the realization, and one second, where is it? Okay, so these are the extra things, but this information will not be available when we are at the time step n minus 2. All that will be available will be I n minus 2 and the action taken, because we can already see what state got realized. Only then there is a way to have some x n minus 1. So these two matter, but the previous two are not going to be useful. So we are going to stick with the weaker condition. The conditional is on these two. Same logic goes for the conditional on the third term from jn minus 1, and the last one is the term with just the noise, and we know noise is independent of everything, so we don't have to worry here at all. Now, same as before, which are the terms where the minimization is actually going to be taking place? We know there's no minimization here. The action is going to be taken after this is realized, and there is no term that affects it. So this will go out completely. This term is also going to be completely unaffected. So these two are fine. We are claiming that this one will also become independent of u n minus 2, and this is the part that needs to be shown. If we manage to show that, then the only terms that will get affected by un minus 2 will be this one term and this second term. And if you recall, this is exactly the kind of structure we had previously also. So if we manage to prove that this one does not depend on un minus 2, it's sorted. So that's what we're going to focus on now. So to prove this, they're considering a lemma. And the idea of this lemma is, let's take two different two different control problems, and then compare those two. Okay, so the original control problem is with the control option available, and the other one, the modified version, has no control. Apart from that, all of these things are the same. These are same. X's would obviously get affected, because whether there is control or not will start affecting in the in the next steps. But initially they're starting in the same way. So let's say we're writing all of them as vectors. So the observations starting from 0 till k could be written as some capital ZK. For the modified game, let's just call it Z bar K. These are the noise terms, and this is the action. Because of this recursive nature, we can write xk as some matrix or something that is applied only on the initial state. And since the initial state is same in both of those problems, this will be the same, because the original matrix is also same. While this effect will only show up in the original game in the form of some GK, and it will not show up in the modified version. But because the noise is getting added, accumulated step by step, that shows up in the following way. Now here the two FKs are matching, the two HKs are matching, for the simple reason that we have taken the noises to be same in both the problems. The only difference in the two problems is there is a control and there is no control. That's it. Otherwise, everything is same and they're starting from the same point. Meaning xk will only differ, xk and xk bar will only differ from each other only because of this component, and there won't be any difference otherwise. So if we use this to try and understand that term, we need one more definition, by the way. Ah, right, not an not a definition. So uk minus 1, the way ik is defined, it is from 0 till uk minus 1. All of these actions are already present in ik, and there are the z's, z0 till zk, or it's zk plus 1. So this is already present, meaning if we were to take the expectation of uk minus 1 given the information, we'd just get the control back, we'd just get the action back. So now let's take expectation of these two conditioned on ik. If we do that, this is what we get. I've just put the symbols, nothing more. And similarly for this one. Suppose then we take the difference between xk and this, meaning we are actually looking at what is the difference between the true state and the estimation of the state, the expected estimation of that state. Then notice the fk's, these and these are same in both of them. So we would get a term like this, fk of oh no, one second, this is incorrect. If we were to do it for both the cases, both the problems, the one with control available and the one without control, we'll see that both of these will turn out to be the same. And the reason for that is this observation. Because of this observation, this term will be gk and this will just be gk uk minus 1, and this will just get cancelled with this, and all we'll be left with would be the difference of this with the estimation here, this with the estimation here, and that exact same thing will be present here also. Now after proving this much, we're still not done, because we already know that ik has uk minus 1 hidden in it. So we still need to verify it very, very cleanly that these two have no dependence on the action uk minus 1. And to do that, we rather focus on the observation. Remember, the difference between xk and xk bar is just the presence of u term. That effect will show up between xk and zk and zk bar also. So let's say that effect shows up as follows. Nk is just some matrix that takes care of it, which means both this and this will be equal to a term like this. But also notice that if we knew zk bar and uk1, uk minus 1, then we can actually create zk, because this nk is something that can be figured out. It just depends on the description of the problem. So if we know the description of the problem to begin with, this is something that we can do very easily, which is the same as having zk and uk minus 1. So we can interchange between the two, we can use one to reconstruct the another. So these two informations are the same. So now notice this component. This belief of xk bar can be written as the expectation over xk bar given the z bar and uk minus 1. But recall, this uk minus 1 was in the other problem. Here we are taking the belief of the problem without any action. So technically this has no effect in this particular case. Meaning this term is strictly independent of the action uk minus 1. And since that's the case, we have managed to show the policy is this particular component is independent of uk minus 1. And because it does not have dependence on the uk minus 1 of that part, the term that we had here, we don't need to minimize this. This is just an extra term. So the effect of all of this jugglery is the next optimal action that we'd get would have the same structure. And this same structure will follow for every k. Meaning, this particular, because this term did not have dependence on un minus 2, we managed to establish the correlation between these three problems. These two problems, we already knew that they were correlated with one another. Here we are able to also establish that in our case, the LQ controller with imperfect information will have a similar form. Some LK will show up, some gain term will show up. So this result has established the three-way relation between these three problems. And this is a very important result. This is something that is used a lot when trying to do practical things. Now, exactly what these LKs and all these things are, you've seen them before and you can go through it. It's just very simple algebra. But if we were to make it into a diagram, a schematic diagram of what is happening, then it's a very interesting result. The block diagram of this problem, the one with imperfect information, is that we have some xk, an observation is made on that xk. While making that observation, there is some noise added to it. That observation is used to is the added information that is added in the information at that point of time. So it's added in ik. Then there's some estimation made. The estimation is this guy. I'll come back to what this component is in some time. This is a different thing altogether. This is the estimation made. And then the estimation is just multiplied by that LK term. And what that LK term is, we know how to get this LK term. And once we know this LK term and we have used it, we have come up with the optimal action for that particular time step. So that's the optimal action to be taken. Since we know the optimal action, the system knows the true state, the next state can be found out, and there's some noise to be added to it. And the cycle continues and it goes to the next state and all the other things. So here, the two components, the controller component and the estimator component, these can be separately designed. And they can be separately designed because this LK, we know we can design using a linear system without any noise in the true state and complete information about the true state. With a problem of that kind, we can just design what this LKs are supposed to be. And for our given problem, when there is some hidden information or some imperfect information, the estimator can be found out separately. And once we have both of them together, we have the next action to be taken. And because these two are things that can be done in separate ways, this is actually called the separation principle. This becomes something very useful for practical purposes. The people who study estimation very strongly can design this component, and the ones who work with controllers can focus on this component, and they can work separately and then just put both of those concepts together, and that's about it. So the aim of all of this is, there is a very nice closed form structure and very nice properties that come out of linear problems, specifically linear systems where the dynamics is given in the form that we have talked about, the information structure is defined in the following way, and so on. This may or may not hold in other scenarios, but in the current scenario, the separation principle holds. Okay, now before I go on and talk about filtering, which is this component, the estimator component of it, let me take an example. This is more like a motivating example and nothing more than that. I'll not go into all the details of the example. If you want, you can try and simulate this. But this is like a more intuitive example to get you some understanding of what is happening. So a simple illustrative example is what I'm taking. This is example number 1. Okay, so I am considering a physics type problem. So let's say there's a unit mass. So my system consists of the physics is that there is some motion to happen there. So let's say okay, let's first define the basic things. So there is positions, that is q, that depends on time. For now I'm writing the regular dynamics, then I'll just use the discrete version and show how it is related to the linear system that we've been talking about so far. Okay, so let's say q is the position, qt is the position. You can think of a simple example like there's a frictionless track, and uh, let's say there's a frictionless track and there's a cart that's moving on it, and some force is acting on that cart. Then the other quantity is the velocity, or the uh, time derivative of q. Let's denote it by it's denoted by v of t. Okay, so now our force, or the control, how the physics is happening, let's say it's defined in the way as uh, its q dot is some ut and some wt. So some force is applied. As the result of that force, its velocity changes with time, and the application of the force is not something that you have full control over. So the change in velocity is with some extra term as well. So there is some slight noisy term that comes up here. So this wt is like a process noise or something. uh, this is like a noise term, or maybe like a modeling error or something like that, nothing more than that. And here this ut is like the control law, or it's or like some sort of a control force. Now if I were to write this as a discrete system, I'm just gonna write it as a discrete system. I'm not gonna talk about how to get that. This is very standard stuff, so if you're interested you could look up how to convert the dynamics of a system to its discrete version, but I'm not gonna go through that part. Suppose you have xk, which is the position and the velocity. So let me denote it with qk and vk. So this is the discretized version, discrete time model. Then using this particular dynamics, you would get that xk plus 1 would be qk plus 1, meaning the next position and the next velocity, which is okay. So this is the first part, and then there is extra term, which is t square by 2 t uk and some noise. So this is the kind of dynamics you'd get. Now you can see, you can compare it to our standard form, which was some ak xk plus bk uk and wk. We have the exact form of ak and bk, and since we have some observation, so let's write the observation, the noisy observation. And this is just some random choice, nothing more than that. So let's call the and the observation variable as z. So it's zk is something that acts on ukvk. And there's some noise component to that. Let's say the observation is mostly of the and it's both. Okay, now that we have uh, the complete knowledge of how to deal with a system like this, we could find out what should be uk, what should be the control, how to apply that uk. We know the optimal at any given point of time, at any k, this uk will be something like some lk times the estimation of xk given ik, and this is something we can actually solve for. Hence the point of this example is this idea of linear systems with quadratic noise. Oh, by the way, I'm assuming that the noise is just quadratic. The cost is quadratic, the same structure as ours. In such a setup, we have this example basically illustrates that standard problems from physics could be put in this system, and they could be really helpful in estimation, in controllers, in coming up with controls, and in fact that is what is used in these types of situations. Okay, any doubts so far? All right, so this was one example that I wanted to cover today. Next, I'll go through the point about filtering just very quickly. And then I'll take one more example of application of the things that we have seen so far. You can go through this example if it's not clear right now. If you have doubts, you can ask me next time. But the idea is, because we know how to handle a system like this, we could easily simulate this and see what happens to the cost, what happens to the x's, how do they evolve with time, how do the positions evolve with how do the positions evolve with time, how can we design the controller to get a certain behavior out of it, and so on. Okay, so next I'll talk about this particular component, right? In both of these problems, the original version and in this example also, how do we deal with this component? Now, this is studied in a mathematical sense, this is not very difficult to study. But in a computational sense, this is a very annoying thing. There are results that allow, for certain kinds of setups, they allow us to solve them in closed forms. But most of the times, that's not the case. But right now, I'm only going to focus on the the theoretical idea or the mathematical idea, not so much the computational ideas. For that, there is this whole estimator type of problems that people work with. Okay, so let me motivate the thing and then I'll get to this part. So now what I am going to talk about is the idea of estimating this quantity, or what is typically called as filtering. So here, just like in the previous case, while solving for the optimal UKs, the optimal actions, we came up with a recursive method, the DP algorithm. It is possible to do recursive calculations here also. Solving them, doing them computationally may not be easy, but writing out what it would look like is still doable. So let's say our state space consists of X. The transition probabilities are some probability of going from state xk to state xk plus 1. We have the observation space, and there is some probability of observations also. So if the true state is xk, what is the probability of making an observation yk? Those types of probabilities, let's say, are known to us. These are the priors of the problem, the description of the problem. And these observations, the y's, are the history of observations for us. This is just notation. Now, as pointed out earlier, this estimation is the solution to the following problem. So the problem is, suppose there is a function on this history of observations. Using this, can we find out the true state at, let's say, the time step k? I'm not focusing on what this n is for the time being. I'll come to the different classes of problems in a moment. And if this optimization is done over the set of all the Borel functions, then this is a standard mean square error type problem. And the objective of the problem is to minimize the mean square error. So whatever this whatever this gamma function will get chosen, depending on what kind of uh, what kind of dependence is there between k and n, we'd be just trying to match them, bring them as close to one another as possible. So if, okay, let's take one scenario. So if k is greater than n, meaning it's something in the future that we have not seen. So it's some true state that we have not seen. We're far away from it. Maybe not too far away, but we're still far away from it. We have not made any observations related to it. But based on whatever we have seen, can we make a, a sensible estimated guess about what it could be? Then that is a prediction problem. Another situation is, if this is how much I've seen, k is
I
equal to
had
n.
I had a thought on this, like
Yeah.
this gamma, if you keep it same, gamma of y1 given n, 1 to n,
Mm-hmm.
and you try to minimize the gap from xk, isn't it the gamma k should be there? Like basically, if in this equation I'm trying to say one function, and xk should,
Yeah.
because
So
gamma k, like as k
it,
varies, gamma k also varies.
it depends, right? That's the reason why this is not written very nicely. This is just written in a very lazy way. In the next part, I'll write it more cleanly. It depends. So how much has been observed and what are we trying to match it to? What are we trying to estimate? That depends on what we have. And is this something that we want to keep increasing? Can we keep improving that? If this is a online situation where we're getting more and more information, so with that kind of a setup, we could have gamma depending on k or n, or maybe some combination. But anyways, for now we're not getting into that part. Okay, this is just, for now it's just definitions, nothing more. Right?
Okay.
So this one is called filtering. When we have seen n steps and we are making a prediction about those n steps only. So We are trying to say at xn what is the true state and what can we estimate about it based on the history we have seen up till that exact same point. We are not using previous history, we are at that same history. If that is the situation, such problem is called filtering, and this is the kind of problem that is of focus right now. Another situation is if you're trying to make a prediction, not a prediction, if you're trying to do a minimization where n is greater than k. So you're taking a point from the past and you're trying to find out, okay, what should have been the estimate of that past point based on whatever you've seen so far. So this is more like a retrospect thing or something in hindsight. So this is called smoothing. Okay, so like I said, we are gonna focus on filtering. So in filtering, what happens is right. Uh, so in filtering, what happens is the solution to this type of a mean square optimization problem. The answer is what we saw earlier. It is this, the estimation, the trying to predict what happens next. Now, notice this expectation. This expectation is basically over a probability of xk given this much history of observations. But this is a quantity that is not known to us. This is not the setup of the problem. This is not a parameter or given in the description of the problem. In the problem, we had some transition probabilities in the state space, some observation densities given what was the true state, but we don't have something like this. So this is a posterior type quantity and we can find this using Bayes rule. So sometimes this is called a Bayesian estimation, and this is what needs to be computed recursively. Okay. Another thing to note over here is this particular expectation. If suppose we take an outer expectation over this, like this, then it just ends up being equivalent to the expectation over xk. This is from the properties of expectations. Meaning this estimator is actually unbiased. It's not dependent on what it got to know. This is an unbiased estimator. So in this particular component, the only focus is on understanding how to get this recursive relation related to the posterior. That's all it is. And right, here it is. So this is our transition probabilities, the state transition probabilities. These are the observation density. Then this is what we are trying to get a recursive relation for. And the recursive relation on this takes a form like this. The proof was done in class. So if you have any doubts, we can discuss that. Else I'll skip the proof for this one.
Yeah, I have.
Oh, okay, okay.
One place, sir has cancelled something that probability of y 1 to k.
Right.
Okay, from both. And he suggested to do something differently. I tried that. Then I realized, like, there should be hidden constraint in the theorem. Like, probability of y at any state should not be 0.
Right, that is like a regular thing. People typically have that in mind. Yes.
That's it. Oh.
Yeah.
Yeah, then apart from that,
that's like a standard assumption you can keep when you're writing things in the denominator. You can keep that as a extra note in the side, and because you're cancelling it, then it's even more important.
Actually, it is not in only denominator, but it's fine. I got it. So more or less, it boiled down that none of the state should be 0. Like observation or probability, that should not be 0. which somehow makes sense for a real-time system. Okay.
Right? There should be some probability of getting that particular observation. Otherwise, that observation will not be in your observation set. That's it. There's nothing more to it.
And maybe because since we are considering continuous thing, to have that zero, I should have point instead of interval. That is fine.
Right.
Interval.
Yeah.
Okay. Fine. That question only. Apart from
Okay. Okay. So the proof is actually fairly straightforward. All we are doing is we are just applying the Bayes rule more than once, and because we have these quantities, we will try to bring them back in. That's pretty much it. So yeah, I'll skip the proof. I'll just go to the last point in the proof. So after the proof is done, this is what it looks like. So there are two things happening here. Uh, 1 second. Let's write it out cleanly. Not write it out. I am just gonna copy it. Okay. So this filtering process can actually be thought of as broken down into two components. The first component can be the prediction step, where you have knowledge up till k step, or you have observations up till k, but you're trying to estimate what is k plus 1, which is this particular quantity. So you are using observation from 1 to k, and you're trying to guess what would be the next one, because this is a term that comes up in both numerator and denominator. Hmm. Right, and this quantity can be written in a recursive form like this. How it is written in that form was something that was anyways discussed previously. Okay, so this is the prediction step, where you're using the information up till now and trying to make a prediction about the next step. Once you have this prediction step, you're just applying the Bayes rule on top of it. So this becomes something like your prior, and then you're applying Bayes rule with this prior, using the possibility of getting an xk plus 1, the true state xk plus 1. Then what should have been the observation? What is the probability of getting that particular observation? Yk plus 1. So then it's just applying Bayes rule on top of it. So this is the measurement update step. Okay, so this kind of standard thing is done in problems which are called LQG, I think, where these quantities are actually Gaussian, and then it becomes very easy and very nice to get closed form for prediction step and measurement update step and so on. Then this kind of filtering is called Kalman filtering. This will be in the upcoming week. But the idea remains the same. It's exactly solving for these two, and after having done all of this, we can use this to get some expression for quantity like this. It'll be some recursive expression, but anyways, we get an expression for this, and then use this with the controller to get the next action. So this would be shown in closed form in another in a particular example in the next class. Okay, so far. Now I'll take another example. So now this is an application of things that we've seen in a slightly different setting. So that you get to see how all of these ideas can be applied to other settings, if they can be applied or not. So far, we have been dealing with one controller or one agent. No learning, but still one agent. Now imagine if it's not one but two or multiple. In such a situation, if we have similar setup, so if suppose we have a LQG setup, but it's a setup with two agents and they're trying to both sort of work together, so this is like a team game problem, then what happens? Can we so okay, another thing, let's say it's not a controller type problem that you have to keep optimizing over some k time steps. It's just one time step at a time. What can you say, can these results or can some of these ideas be forwarded and applied to such a setting? Is the rough idea of the question clear, what we are going to work on now?
Could you repeat the last part?
Yeah, so now what I'm saying is, suppose I'll repeat the whole thing only. So we have LQG team game. Team game means there's more than one agent, and I'm gonna take a simple case of just two agents for the time being. So let me draw what the game structure is like. Let's say there is some true state of the world. Okay. Just give it a second. My iPad is stuck. Okay, anyway, so what I was saying was, so far what we have seen is we are taking a problem with k time steps, and with each time step there is a DP algorithm applied, some optimization to be done, and then the next action is decided and it keeps going. Now I'm not talking about that situation, it's just done once, but there are two people who are doing it. So they, since this is a team situation, they're both trying to optimize the same thing. They're trying to, if it's a minimization, so they're trying to minimize the same quantity, and they're trying to do it together, but they have to take their actions separately. Okay, it's that kind of a setup. So now let's say there is some true state of the world. um, this is a Gaussian, and let's take this to be some vector, so let's take it to be some RD. From here my agents make some observations. I'm going to write those observations as A and B. These observations depend on xi. The dependence is A is some linear transform of xi, and similarly B is also some linear transform of xi. HA and HB are full rank matrices, and let's say the A and B that I get are they're both Rn. Right, they're both Rn. Meaning this one is Gaussian, these two also become Gaussian. The kind of Gaussians they'll become would be, can you tell me what kind of a Gaussian they'll be? So A will be, the mean will not get affected, it's the variance that will get affected, and the variance will become,
So it will be like the dimension will change. Sigma of RD comma HA. Transpose, right?
yeah, HA transpose, right? And similarly this one. Okay, so this is, I'm first describing the problem, or maybe I should just write it as the main part only. Same thing will happen for B also. So B will be HB transpose sigma HB. Whatever, it's still Gaussian. So what are the steps? We started with psi. We got AB. AB are the observations. Now, based on those AB, some action is to be taken. So let's say action by agent A is X and the action by the other agent is Y. This is the state, this is the observation, and this is the action. Or similar to our language, this is UAUB. And then there is a cost to be worked on. So let's say that cost is something that depends on X, Y, and the state. Now, I don't know what the dependence is, so I'm saying that it depends on some gamma A, gamma B. Okay, and I'm assuming the gammas are some functions from Rn to R. Okay, so the x and y's are scalars for me. They don't have to be, but for now I'm taking them to be scalars. And the next step is to get the loss function. So the loss function is okay, there's a matrix, the 2 cross 2 matrix here. Transpose. Some Q matrix here, okay? Some 2 cross 2 matrix. Some other matrix of the appropriate dimensions inside. So this would be a matrix of dimensions 2 cross D. This is how my problem is. And the overall minimization is over both of them. Now it's over gamma A and gamma B both, and I am taking the expectation. So expectation would be over everything where there is a probability. So there is a distribution here, there are distributions here, and how are these chosen? Let's say they are chosen in a deterministic fashion, so no further here, but up till these 2 points we'll have to take the expectations. So the expectation is over the sigmas, and let's say AB given sigma of this L. Okay, so this is the goal. So this description that I've given is a standard LQG team problem. Okay, so if you compare it with what we have seen so far, the catch here is there are 2 agents, 2 learners, 2 actions, but both of them need to be taken at the same time. It's just happening, all of this is just one time step. It can be extended to more time steps, but if we understand it for one, extending it is not the difficult part. It's just this much that we have to understand. Now, there's one component that I'm going to skip in this particular proof. You can try it out yourself, and it's actually very easy to do, but I'm gonna not talk about it in more detail. Is that instead of doing both of them at the same time, I'll do one at a time and still be able to make the final argument at the end. Meaning, so there are 2 kinds of optimality in team games that happen. Okay, so one optimality is when both of these are optimized together. One is both of them are optimized separately. So okay, let's write this quantity as j of gamma a gamma b. Right, this is some quantity that will depend on the choice of the functions that were taken to choose the next action. So it depends on gamma a and gamma b. So first type of optimality says if I manage to find the best one in both of them, this star symbol means I found the best one in both of them. This is going to be less than anything else. But I found them together for all gamma A, gamma B. The equality is when the optimals are matching. When gamma A and gamma B are the optimal strategy choices. Okay, so this type of a problem is what we are actually after. This is team optimal. There's another one which is, oops, sorry, yeah, there's another one where you're like, okay, let's fix the action of the other one and optimize for one of them and then repeat the exact opposite situation. So here I'm saying, let me fix B. Okay, B is not something I'm changing, but A is something I'm changing. And again, this should hold for all gamma A. So this is one. The other version in this would be the opposite, where A is something we have fixed and we're not bothered by it. Okay, so since we are fixing on this side. We're fixing on this side. We'll vary on this side. So let's do it like this. We're varying gamma dash, B dash, and here we're varying A dash. So here we're looking at all of the other possibilities and we see that doesn't help, and this is also something we're varying and seeing. So these are two different types of problems. I'm leaving it as a claim. In LQG games, with second type of optimal, then the same thing is first type of optimal also. This part I'm not going to prove, but what I am going to show is the structure of this gamma A star and gamma B star actually is linear. So both of them are of this kind. Gamma B of A is something linear. Some gamma A transpose. Okay, so now this is more like a vector, nothing more than that. This quantity is just a vector. And A. And similarly, so do you understand what we are going to show and what we are going to skip in this particular problem? There are two types of optimalities. We are not going to argue that they are the same for this problem, but if we find the optimal, they are the same. But what is that optimal is what we are going to focus on, because finding that optimal, to find that optimal, we can use DP algorithm and all of these things that we have seen so far.
Okay.
Clear?
Yeah, yes, okay.
Okay, right, alright. So this is the part that we are going to show. So since the process to focus on these requires us to start with the person by person optimal, let's focus on finding the person by person optimal itself. So to find the person by person optimal, what do we have to do? We have to fix one of them, right? And if we are fixing one of them, something conditional will come up, right? So what we are doing is, let's say we fix no let's fix y, was it right? Let's say this is fixed, whatever it is, one function is fixed. So now our problem reduces to minimizing over just gamma a, and this is ab given gamma, or let me not write all of that anymore. We know what we are doing the expectation over of L x y, or rather gamma a. But here we are going to put a conditional, and conditional is whatever information we have, and here for us the information is just the observation a, nothing else. So we are going to condition it on a, and also since we have conditioned it on a, this quantity becomes some kind of a function of a. It does depend on what gamma is chosen, but still this is still a function of a. Or maybe if I were to write it more carefully, this is gamma a, since we have already fixed the other action. That's no longer a parameter here. Okay? So we do exactly what we have done in DP type problem so far. This is still the DP type version only, and this is on top of that it is quadratic. So what we do is, next we just write it down. L had terms like this, right? I can expand these terms and write them more cleanly. So let me break down Q in the following way. So Q is some Q A A, Q A B. Remember this Q matrix is semi-positive definite. So with that we would have x square QAA, xy. Remember these xy's and all of these things are just um, some scalars, some functions that give us some scalars. So for now I'm not too bothered about the transpose and all those things. And I'm taking Q to be positive semi-definite and symmetric also, that's by default. So this happens. Then there is okay, let me, instead of writing xy, let me write them as gamma a, gamma b. Gamma a square okay. Another thing, I'm breaking this s in the following way. So let's say there's a SA component and there's a SB component. Each of these is like 1 cross D. So the vector version. So we have gamma A of A, SA psi, and there's right, and conditioned on A, and then this. Now there are terms, for example this and this, that have no dependence on gamma A whatsoever. So these things don't need to have any optimization done over them. The other terms have gamma A in them, so that's the important part. So we can rewrite this as this is the terms without any dependence on gamma A, and then the terms with dependence on gamma A. Then there is and it's all conditioned on A. What do we do next?
We can differentiate and
Yeah, that's it. So if we're gonna try and just differentiate this part, this is a differentiation with respect to a function, but since the functional dependence is very simple, we can just take a simple derivative and not worry too much about it. So when we do that, we would get, so the first term would give us gamma A Q A conditioned on A. This is the first term. Second term would have Q A gamma B of B, and there's expectation over this condition on A, and we would have to equate that to 0. Now notice this part. If we know what the observation is, using that observation we can find out what this exactly is. So there's no need for an expectation on top of this. This is just it. This is there. So this term just becomes gamma A of QAA. But no further simplification can be done on the other part, at least as of now. Right? So this is if we did the optimization with respect to gamma A. If suppose we repeat the
we can take it out as SA gamma, right? SA into gamma, we can take it out. That's psi, sorry, psi. SA into psi, we can take it out. And since expectation of psi is independent of A and becomes 0, isn't it?
No.
Because psi is considered to be a Gaussian, right? So,
Psi
like
is
there is a
considered.
plus, right? So we can split into two, linear property of average.
That's fine.
Then second part, which is SA into psi. SA and psi are independent. Then 0, because psi mean is 0.
Okay, yeah, that's correct. So you're saying this part vanishes. SA is something that doesn't depend on anything. The state should not have, right, it's going in one direction, so knowing A should not still be able to tell us anything about or psi. No, actually we can't by default take this to be 0. We would have to find out what is that exact Gaussian form, because this is a conditional Gaussian now. Even though it's going in one direction, but it's still, because of posterior properties and all of that, it could still have some dependence. So it might
Because,
not be 0.
because if you see Bayesian graph logic, A is
Hmm.
known. So some after stage is known. Now gamma is independent of A. Maybe I need to check this, but I'm
Yeah.
feeling. See,
Anyways, that doesn't change the point that I'm trying to make.
okay,
That
okay.
might turn out to be 0, or that might be some constant. That's still not something to worry about.
Fine.
Anyway, so remember, all that I'm actually interested in proving is it will be something that is linear. Doesn't matter in what. It's just going to be linear in A and B. Some function of A and B. So
Okay, okay.
that's all that matters. So this is not that problematic. Then if we were to repeat the same process but optimize over gamma b, you'd get something similar. 1 second, I made an error here. No, so this is fine. This is not that big of an error, but anyways. Right. So if we were to repeat it for the other one, for gamma b, we would get something like this. QAB and QBA are same, so it doesn't really matter. SB Xi A, this should be equal to 0. Now they have cross dependence on each other. So fixing one and getting another, and then fixing one and getting another, it's like a cyclic loop. So we can just focus on only one of them. Let's say, because we're ultimately trying to prove that they have to be linear, let's say one of them, so let's say this one is actually linear. If this one is linear in B, then that means this quantity will be something that will get picked up from some Gaussian. Okay, let me go back one step. Where were we in the description of the problem? Remember, A is a Gaussian. If gamma A of A is linear in A, that just means ki it's going to be sampled from some Gaussian. X would be sampled from some Gaussian in some sense. So this
Right.
quantity is a Gaussian. And this one we already know is a Gaussian. So now this is a standard point. If this is a Gaussian, this is a Gaussian, and this is just a linear combination, some linear combination of two Gaussians. So this is jointly a Gaussian, even with condition on A. That means this quantity has to be linear in A, the function that is what it is conditional on. And if that happens, that linearity will be used here, and this will become linear.
This QAA will be invertible.
Hmm? These are
Q
numbers.
numbers. Okay.
So yeah, so if they're 0, then we are sorted.
Mm,
Then we won't try and invert them.
okay.
Otherwise, it's fine,
Yeah, fine, fine. It's
right?
linear now.
Which means both of these. So I'm skipping the steps about exact estimations and solving and simplifying this, but because this whole quantity is a Gaussian, and it's some expectation over some Gaussian given something, so this is going to be something that is linear in A ultimately. Oh, and here it will be something that is linear in B. So we will get some gamma A transpose, some vector, and linear in A, and so what we managed to solve for is the person by person optimal thing, or what we managed to get is the solution for the second optimal. Now what we can do is we can use this and try to see, because our loss function is quadratic, so it is strictly convex. We can use that idea, write it down, take the expectations and simplify a little bit, and we'll be able to show very easily that because they are person by person optimal, these strategies or these actions have to be also team optimal, the first kind of optimality. So the idea some of the ideas that we saw in the linear systems actually even translate with minor caveats, minor things to be careful about, even to systems with more than one agents. Here I've dealt with just two agents. You could do everything and talk about more than two agents and have a specific example. So this is the one with LQG, the Gaussian one. If it is not Gaussian, then you'll have to be slightly more careful, but it's still doable. Okay, so this was the second example that I wanted to show today. Now let's take a quick recap of what we did and then we can wrap up. Do you have any questions?
No.
Okay, great. By the way, if you notice the assignment for this week, it's mostly definition type questions. There's, I think, only one question where you have to solve a little. Otherwise, it's definition types. So, not much to worry about there. Okay, so today we made one very important point, and I'll show it through this diagram. We saw uh, that the game with the control problem with LQ, linear dynamics, and alright, linear dynamics and quadratic cost with imperfect information. In this type of a problem, the optimal strategy or the optimal action that we get is something of this form. It There is some constant that comes up in front, and it depends on the belief of the current state given the information up till then. Now, if we were to compare this same thing, the same result, with results where there was perfect information, meaning the states were known, there were no noisy observations or anything, the states themselves were known directly to the controller, then the optimal action would be to use the same L. So the L's would be same here. So this is the controller component. This is same in both of them. Here it would be the actual state which it will get multiplied to. With imperfect information, there'll be a belief of the current state. And this not only holds for n minus 1, it holds for all k's, starting from k equal to 0 till n minus 1. And we also know that the same optimal action is the case even if the LQ problem with perfect information had no noise in it. Meaning, presence or absence of noise is also something that is not a very big problem. This is specifically true in the kind of structure that we have defined in our problem. If we change the structure of the problem, this may or may not hold and it would need to be verified again. But this idea becomes very helpful when we are dealing with more nuanced and difficult problems. As an example, we saw what happens if we have an LQ control problem. Instead of a control problem, it was a team game problem, and a team control problem rather, with imperfect information. Then we saw the results were still similar. Similar, not same. That's the slight catch here. That's about it. But the ideas can be translated and applied in different settings. That's the takeaway from this lecture. And the core thing that we used to establish this is this particular component or this particular term. This is the term about, or this particular term, this is the term about the difference between the state and the estimation of the state. So it's like the error in the state estimation. We showed that this is something that does not depend on the action, and because it does not depend on the action, meaning it does not depend on uh, so for the time step n minus 1, it does not depend on the action previously taken to get there. The error does not depend on the action. The states do, the individual states obviously do depend, but it's the error, the state and the estimation of the state, that is not getting affected by the action. Meaning, this difference is something which is coming because of the noise in the problem itself. It's an intrinsic thing. It's not happening because of the actions taken. It's not the effect of the action that is getting accumulated over the next steps. And because of this particular point, we were able to show that. Okay, I'm not going to talk about this again. We were able to show that the optimal U star will have the same structure in all the time steps k, meaning the optimal policy is the same as the optimal policy of the perfect game, the game with perfect information, as long as we take the conditional expectation of the state given the information. So if that's the quantity we take, it's the same thing. So this L and this, these are two separate quantities. This can be calculated in more than one ways, and this is something that can be calculated separately. Because of the segregation, the separation between these two, and that they can be found in different using different methods, allows to come up with this separation principle, which says that the controller can be designed separately and the estimator can be designed separately. This separation allows people to work on two different classes of problems independently and then just merge the results together, computationally and theoretically both. This is true for problems where such separation is possible. Specifically, we have shown it in our kind of setup. Then we looked at what this estimator really means. So we saw that this estimator is the one that minimizes some mean square error. Here, just to make the point, the estimator was taken to be only on the history of observations. We could have the actions in between as well. And a recursive relation was established on these. The xk given whatever history of observations is seen so far. And this particular component can be understood in two steps. The two steps are, first there is a prediction step where using observations from 1 to k, we are trying to estimate what would happen at k plus 1 step, what would be the next state. That is the prediction step, creating a belief for what is next, and then using that and writing it as a base rule for the actual observation made at k plus 1, the actual state and the observation made at k plus 1. If this is done in a setup where the x's, the dynamics itself is linear but the noise and so on, for example, are Gaussian, then there is a well-known closed form for these types of things, and that comes under Kalman filtering, and this is something that's going to be discussed in the upcoming lectures. Okay, and then obviously we talked about this particular example. Okay, with this I've covered week 7's tutorial. Do you have any doubts?
One question I had, like when reward is depend on the history, like previous.
Right. So that one is something that can be handled with whatever machinery we have so far. But let me still illustrate the point. So if your reward was something that was dependent on history would have s starting from 0, a0, st minus 1, at minus 1 till st. Okay, so if this much is known and the reward depends on the history, the action taken at that time, right? You'll only know the reward once you've taken an action and you're going to the next step. So you will have to have some AP, and also you'll have to have the next uh, state that you're going to. So when you have all of that, that's when you'll take the reward. That's when you'll take the action, get to the next state, and get a reward out of it. It could be either this or this. These are the two possibilities. And you can go from one to another by just expectation and nothing else. Like you can go from here to here. You can just take expectation with respect to the transition probabilities and you're okay. Okay, so this is one point. Now what actually happens here is, remember, in the language of MDP there was the word Markov decision process. Markov means at any given time your decision is based on just the previous time step. But if your reward depends on the history, it's actually not using just the information at the last time step. It is using something from behind also. Right? So depending on where you got to that state now matters. It's no longer pure Markov. So the process itself is not Markov anymore with the reward in place. So it's not a Markov decision process in the current form. So in such a setting, the solution would be, so the solution is standard. We have seen this kind of solution happen. Solution would be to, you know, define some I, let's say the information. Okay, so I is I t minus 1, at and st. Same stuff. Now what I can say is, what if this is the new state? This whole thing is the new state. And repeat everything.
Recursive.
Yeah, and we've seen how to handle a situation like this. So even without directly dealing with a situation where reward is history dependent, we have in a roundabout way actually dealt with this already.
So moral of the story is, if you put condition over H state, suppose history is known. If I put condition like an information, then it's a Markov. Is it?
Yes. Because see, you should be making your decision based on what you are observing at that current time step. That is what Markov property means. You cannot use the previous history to go from there. So the process itself should be Markov, and the rewards hence should be of that same form. So to deal with it, the way is to make your state be the history itself. Then you can handle it. But if you're doing that, then that is the same as the kind of problems that we've been seeing. Right? It's very difficult to handle, but yeah, it's technically possible. There's nothing stopping us from having problems of this kind.
Okay, thank you.
Yeah, you're welcome. Alright, then I'll close here.